This is a walkthrough of the 2020 Electrical Systems exam, starting with question 1. This is a straightforward question. We're looking at using the equation straight off your equation sheet. Vmax equals the square root of 2 times VRMS. What we've got is a AC circuit, and we know that the voltage is going to be doing some sort of sine wave. So the average, the RMS is like an average voltage. That should give you the same power output. Now, if we then substitute and solve, .414 times 65.0, which is 91.91 volts, or 91.9 volts to 3 significant figures. That is worth an achieved point to get the correct answer. Alright, question 1b. So here, firstly you're going to need, and it says a phasor diagram may be useful. I think a phasor diagram is actually essential. So we have 3 phases in our possible system. We have the resistance phase, which is also the current. We have the inductor phase, and we have the capacitor phase. And if this set of phasors is rotating in this direction, this shows us that the inductor phase leads, so it gets to this, let's say, location down here. The inductor phase gets there first, then the resistor phase, then the capacitor phase. So now we can put on this our Z vector, our impedance vector, and we've been told that the angle, which is also the same as, in terms of angle, as the power supply. Okay, so the power supply and Z are at this angle, the resistor voltage, the reactances are at these angles, and the current is in phase with the resistance. These, of course, are 90-degree angles in here, but key thing here is that the impedance leads the resistance, or leads the current rather, which is the same as the resistance, by 35 degrees. The supply voltage leads the current by 35 degrees, so the impedance leads the resistance by 35 degrees. Now we've got a solvable triangle for impedance. And this one here we have a value for 1.50 times 10 squared. So SOHCAHTOA, which one are we using? We've got the adjacent and the hypotenuse, so we're using this one. Cosine of theta equals A of H. That's what CA means, so cosine of 35 equals 1.50 times 10 squared over Z. Rearrange, and we get Z equals 1.50 times 10 squared divided by cosine of 35. Z equals 1.50 times 10 squared divided by 0.819. Z equals 183 ohms. Alright, and we have an achieved point for a labeled diagram, an achieved point for a correct answer, and if you get them both, you get a merit point. Alright. And now we've got this next one. Let's have a look. Okay, the inductor has an inductance of 0.380 henries. So the starting point is to think about our phases again. We've got this situation. Actually, why am I doing that? Let's just draw this up a bit different. Okay, so we've got our situation where we've got some sort of inductor reactance, we've got some sort of capacitor reactance, and between the two, they're leaving a total reactance here. So when we add up the inductor reactance, the capacitor reactance, say the resistance and the inductor reactance, they produce a resultant phasor for the impedance that looks like that. And so we've already worked out, we know what this is, and we've worked out Z here as, no, we haven't worked out Z yet. Okay, so there are things we can work out from here in any case. So we've got this, and we know that this angle here is 35 degrees. Okay, so what we're actually wanting here is, to start with, is the total reactance. Now the total reactance is XC plus XL, which in this case, because they're in opposite directions, is actually XL minus XC. And we can use SOHCAHTOA again. SOHCAHTOA. In this case, we've got tangent of the angle equals the opposite over the hypotenuse. So tan 35 equals x. That's this distance here, x over 1.5 times 10 squared, x equals tan 35 times 150, and that is 105.03 ohms. Okay, that's a starting point. Now we can work out the inductor. The next thing we need is some equations from our worksheet. So the inductor reactance equals omega L, the angular frequency, times the inductance, and the angular frequency equals 2 times pi times the frequency in hertz. Okay, so those are both on our formula sheet. We can do a substitute and solve. And we get 119.38 ohms. Now it's really important that you use pi to like 4 decimal places, because at least 3 decimal places. Don't use 3.14, use the pi button on your calculator, for example. Otherwise you get slightly different answers, and I don't know how crucial that's going to be to the examiner, but it will affect the answers overall once you start doing multiple multiplications in a row. We wanted a similar thing. Now, so now we've got the inductor reactance. We can work out the capacitor reactance by using this formula here. So we've got that XL minus XC equals 105.03, and we now know that XL is 119.38. And so now we can, so we're going to bring this to this side by adding XC to both sides, and this to this side by taking 105.03 off both sides. We get XC equals 119.38 minus 105.03. And that leaves us overall that XC equals 14.35 ohms. And lastly, we now need to work out the capacitance. So we're going to go back to our formula sheet again and see that XC equals 1 over omega C, and again omega equals 2 pi f. So XC equals 1 over 2 times pi times 50 times C. Actually, let's sub in here. Yeah, 14.35, and we find that we solve this out, we get C equals 1 divided by 14.35 times pi times 2, I just put that in the wrong order, times 50 equals, and we come up with a number of 223 microfarads, 10 to the minus 6. That's what a micro is, to 3 significant figures. Okay, and now let's have a think about how this gets marked. It was quite long, and there's a reason for that. This is the excellence question. So to start with, there's a number of different things that can get you achieve points out of this. But the crucial ones that you would really want to get are this here. So that X, the total reactance, equals 105.03 ohms. That is a good achieve point. Also up here, could have got an achieve point from this. So even if you couldn't figure out the total reactance, if you knew that you could figure out the inductor reactance, then you could get an achieve point, which is 1/8 of the way to passing the exam. And then if you get to here, this is worth a merit. And if you get to here, this is worth the excellence. Okay, so critical if you wanted to get an E8 or something out of this question. Alright, this last part of the question. Well, what's our critical stuff? Explain what changes need to be made to the frequency of the signal generator to bring the circuit to resonance. So let's make a statement to start with. Resonance happens when the current is max, which happens when the inductor, well, let's actually just write this way, XL equals XC, so that XL minus XC equals 0. That's the important thing, that ultimately we want, they cancel out, the two vectors adding up cancel out, And that will give us the situation where the impedance equals R. Okay, that's the key criteria. Now, we can think about this in a range of different terms, but let's think about what this means. So compared to where we were, at the moment we had XL equals omega L equals 119.4 ohms, and XC equals 1 over omega C equals 223 ohms. So XL must increase and XC must decrease increasing frequency. Increasing omega will increase this one, increasing omega will decrease this one, will increase XL and decrease XC. Therefore, we should, is it we? I'm not sure. Increase have I got that right? What am I talking about? I've completely butchered that. I'll tell you why. See this here, 223 ohms? No, I don't. That was 223 microfarads. Let's get rid of that. Let's just go down and delete all of this stuff out of here. I thought something was wrong. It's not 223 ohms at all. You've got to be careful sometimes with transposing, particularly when as rubbish as I am at keeping things tidy. Okay, so let's try this again. This was only 14 ohms. Alright, so XL must decrease and XC must increase, decreasing the frequency will decrease XL and increase XC, therefore decrease the frequency. Now there is another way to do this. That's a sufficient answer to get the merit point that is available here. There is another way to do this. You could start with a formula off your formula sheet. Well, I'd make this statement at the top still. Resonance happens when the current is max, etc. But then you can use a formula off your formula sheet. 1 over 2 pi times the square root of LC. So this is also possible because you've already calculated the capacitance and the inductance. Times pi, let's just use pi here, times the square root of 0.380 times 223 times 10 to the minus 6. And if we calculate that, we get 17.3 hertz. And you still got to say, therefore, decrease the frequency. Okay, now let's think about the way this is marked. So there is achieve points available all over the place here. There's an achieve point here. There's an achieved point available for kind of this, and there's an achieved point available for kind of, actually it's not so much for that, it's these. You still had to have this, you could have this, you could have this. There's an achieved point for that or for that, but you can only get one achieved point overall. It's just like if you said anything particularly important, you got somewhere. Now if you said all of this, this was worth the merit, and if you said all of this, this was worth the merit, but you had to include decrease the frequency. Okay. Now remember that an achieved is basically worth 1 point in the exam, a merit is basically worth 2 points in the exam, and an excellence is basically worth 3. Each part of the question can only be worth an A, an M, or an E. So, for example, part D here, you could get 2 points for a merit, but that's all you could get. Or you could get 1 point for an achieved, and that's all you could get. For part C, you could get either an A, an M, or an E. For part B, you could get either an A or an M, and for part A, you could get just an A. You add all that up, you can get up to 8 points for a question. Alright, so that was question 1. Let's have a look at question 2. Okay, so we start pretty simply. So here's our, what is it? It's got an inductor and a resistor in series with a DC voltage. It's part of a car ignition system. Over here you've got the spark gap. You're given various details. It's a 5 Henry. Most of the details I think are on here though, so you almost don't need to read it if you can interpret the diagram. There's a switch here, and so what it says is state the voltages across the inductor and the resistor the instant after the switch is closed. So the switch is open, now goes to switch closed. That means it applies 12 volts across this here, and a current should start to flow. But of course what we might know if we just think very quickly is just sketch a couple of graphs. I'm just going to sketch one. This doesn't have a capacitor in it, but if this was a capacitor, we know that it would charge up, whereas if this is a inductor, it does the opposite. Our inductor starts high, it reacts to the rapid attempt to increase current by producing a high initial voltage and then drops quickly and eventually peters out to 0. So we need to remember these two responses that capacitors and inductors have. The inductor responds to a large increase in a large rate of change of current. So we go from having no current to having instantaneously. We would normally, without an inductor, have a current that we can define based on these, and this means that we get our maximum inductor voltage right at the start when the rate of change of current is highest. So at the instant after the switch is closed, what happened there? No. After the switch is closed, well, immediately the inductor voltage is actually going to be 12 volts. VL equals 12.0 volts, and leaves no voltage for the resistor at that particular time. Okay, and that's because there's essentially an infinite rate of climb of current at that moment. So the inductor takes the maximum voltage available. Now, If we want to know what that would be worth in the exam, get both those right, achieved point, just one achieved point. Okay. Here's part B. Now, explain why the current takes time to reach the maximum once the switch is closed. So let's have a look at the sorts of things we can talk about. As the switch closes, there is a very high change in current over change in time, so rate of change of current. Therefore, and you can use an equation if you like, therefore the self-inductance causes a large opposing EMF, also called a back EMF sometimes. And opposing, we mean opposing the current. So that slows down the build-up of current. All right. And that's all you actually need for this. You could also probably calculate the time constant. You could talk about the current initially being 0 and building up as the voltage across the resistor builds up, that being the voltage left over. But ultimately, this is the 2 points you really want to have, which is this point here, that you've got very high rate of change of current, and that you've got this causing a large EMF that opposes the current. And if you have both of those, you get a merit. The important thing is, do not say induced current, because if you start talking about induced current, they'll start thinking he doesn't know what he's doing, or she doesn't know what she's doing, and you can't get a merit if you mentioned induced current. In this case, the current that is there is being driven by the battery. If you start talking about current being induced in the other direction, then you would be showing that you're not really thinking about what's happening in the circuit. There's no current reduced in the other direction, or induced in the other direction. There is a voltage induced that reduces the current going from the first direction. You might get away with it if you made it really clear that the induced effect and the direct effect from the battery netted off against each other to leave a total current in one direction, like a hypothetical current being induced in the other direction, but I just don't want to go there really. Okay. How about this question here? Question C. What are we asked for? So the circuit shows a simplified, same circuit. Now calculate the circuit current one time constant after the switch is closed. So you need to know what the whole time constant thing's about. We are going to need several different things. Firstly, we could think about what does this really mean. So this doesn't get you any points, I don't think, but let's just have a look at what this means. So eventually we're going to have our Imax. Right? Eventually we're going to have our current, and it's going to start at 0 because that's what inductors do. They stop the current building up instantaneously, and it's going to reach out towards Imax. And if we remember our graphs correctly, there's a point here, 0.63 of the way to Imax, and this is reached after one time constant. And then, if we went 0.63 of the way from here to here, this would be our 2 time constant. And so what we're after is thinking about what is one time constant. Actually, we haven't been asked to find one time constant. What we've been asked to find is what is the current, calculate the circuit current one time constant. So the first thing we're going to need is Imax, and then the second thing we've got is 0.63 of Imax. So to find Imax, V equals IR. It really is that easy. I equals 12.0 divided by 22.0. This is a DC circuit, so don't get stuck thinking about adding reactances or anything like that, and there's no such thing here. This is a DC circuit. So Imax is 0.5454 amps. Okay. And now, that's not the answer though. We want after one time constant, after one torr, I equals 0.63 times 0.5454, which is 0.3436 amps. And 0.344 amps to 3 significant figures. And if we have a look at what this is worth, this is an achieve point, this is an achieve point, knowing that it's this times Imax is an achieve point, and getting to the answer by a correct method is a merit point. So if you get the whole shebanger, you get a merit point. Otherwise, you might get an achieve point either for working out the final current or for stating that the current after one time constant is 0.63 times the maximum current, or the final current. Okay, next question, part D of question 2. So, spark plugs need a very high voltage of nearly 20,000 volts to produce a spark. Explain why a spark is produced when the switch is opened, but not when it's closed. So there's the first thing we can say here, which is that let's deal with but not when it's closed. So when switch is closed, the voltage across the spark equals 12 volts. Not enough to spark, okay? If you need 20,000 volts to spark, then 12 volts is not enough. And Kirchhoff's law will tell you that, because when you close this, one loop of the circuit is here, another possible loop is here, another possible loop is here. What that tells us is that this voltage from here to here is the same as this voltage from here to here and from here to here, which is 12 volts. Okay. Second, when the switch is opened, now this is important. So when the switch is opened, the current stops. Therefore, and this is the important thing, delta I over delta T is very large, and the EMF equals negative L times delta I over delta T. Therefore, the EMF from the inductor is large. Okay, so that's crucial. So we can get a large voltage out of the inductor. Now, what else do we possibly need here? Well, firstly, we've got to show that this large voltage in the inductor ends up on the spark plug. So Kirchhoff's law says that whatever voltage we gain here has to be lost somewhere else in this loop. Voltage of the inductor is applied to spark gap by Kirchhoff's law. Because, and if we think about this for a moment, in Kirchhoff's law we've got a 22 ohm resistor here. The spark gap here actually acts as a very large resistor. Well, you can think of it as a very large resistor. So the voltage gained here from the inductor as it discharges is lost here and here, but most of it is lost here rather than here because this is a much larger resistance. We've got to assume here that the switch itself does not have a small gap once it's turned off. We'll just put Kirchhoff's law in brackets. And so that's a second point we can make. And a third point I think we should probably make is that there is a very short time constant. So why do we get a spark, not just a slow discharge? So torr for the circuit equals L over resistance. And in this circuit, R equals 22.0 ohms plus, let's put R total in here, spark gap. The time constant is now very short due to the high resistance of the spark gap. So firstly we've got a instantaneous change in current in the circuit, then you've got a circuit here with a large resistance, so a very short time constant, so the discharge will be very quick. Okay, and you put all those three things together and you can get a good answer. Now, what I can't remember is, did we already have, I think what you have to have here is, this is worth an A, 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 you need these ideas, you need all of them for E, and you need these plus one other for M. Okay, so you need to say this, that 12 volts is not going to be enough, and that when the switch is opened, the change in current is very large. You need both of those, plus that the voltage from the inductor is applied to the spark gap, or that the time constant is very short for M. You needed all three different aspects for E. Okay, so it's quite a tough question to get the excellence out of, I think. Alright, the disposable camera flash. So hopefully we've learned that with the camera flash we have two switches. We should have seen this in the video. The first switch you close to charge the capacitor, then you open that switch and close the switch B to discharge the capacitor through the flash bulb. Okay. So sketch a graph in the space below to show what happens to the size of the current over time as the capacitor discharges. Now when you sketch a graph here, you really need to make sure that you label your axes. So current over time, so let's just whack that in, current and time. What do we know? We've got a Imax up here, and it's going to go like this. Why? Because, well, it's a capacitor, so it doesn't have any effect on the circuit initially. The current is going to be driven by whatever is the values of the other components in this loop are, but as current tries to flow, it starts building up in the capacitor here, and a voltage in the capacitor builds up that opposes that current, which means that the current slowly drops over time. And if we wanted to, we could throw some extra details in here, like our one time constant line, and that this is 0.37i, but you don't need it. That graph alone, labeled up properly, was worth a... Oh no, it's not yet. Sorry, we've got more to go. And we've got more to go. We've got, there was the first part, state what determines the size of the maximum current. Well, initially at the outset when the capacitor is not stored, so the maximum current happens at the beginning before the capacitor is charged. V equals IR tells us what happens at that point, because at that point the capacitor has had no impact. So the only other things in this circuit are the voltage and the resistance. I equals V over R, therefore supply voltage and the resistance determine the initial current. Alright, and there's an easy merit question to start off with in this one. Compare that to the hard excellence in the last part of the last one. So this is worth an achieve for your labeled graph. You only needed the shape of the graph and the labeled axes. So you need this, and the shape. And over here we've got supply voltage and resistance determine the initial current. That was also an achieve point. Both equals merit. Okay, next. Next we have a question about energy. Calculate the energy stored in the capacitor once it is fully charged. Well, let's just go with these things as they come at us. So on our equation sheet we have E equals a half QV, and we have Q equals CV. We could combine the two directly and get E equals a half CV squared, and we do our calculation on that. We have C and we have V. V squared is just 9, so half times 1.2 times 10 to the minus 4 times 9, and we get 0.0540 times 10 to the minus 3 joules. Right, so that's the first part. Calculate the energy stored in the capacitor once it is fully charged. It's fully charged once it has all of the voltage in the circuit and the current has stopped flowing. Compare this with the energy supplied by the battery and account for any difference. Now, you've got a choice here. You can work out the energy supplied by the battery. This is a good way to start. So energy supplied equals QV, which is, well, this was a half QV, so energy supplied equals QV, which is twice that, which is 1.080 times 10 to the minus 3 joules. And then compare the two. It is half the supplied energy. All right, and account for any difference in the energy. The energy was lost as heat due to the current flowing through the resistor. Through the resistor. And I think that is all we need. What you've got is, let's have a look at our, this is with an achieve point in our marking scheme. This is with an achieve point in our marking scheme. This is with an achieve point in our marking scheme, or this is also, and we need 3 for M. 3 of those for M. Okay. Next. Alright, so now Emily decides to try and, or to at least think about making a capacitor to be this 1.2 times 10 to the minus 4 farad capacitor. So that's 120 microfarad capacitor. So she's going to make this with some stuff. Now this uses a formula from your formula sheet, which is about the fundamental characteristics of a capacitor. So you go and find that, and you get C equals E0, the permittivity of free space, times ER, the relative permittivity, times the area, all divided by the thickness of the dielectric, so the distance between the two plates. This is the area, overlapping area of the plates. Her thing is going to look something like this, with a layer sandwiched in between, and then another sheet of metal foil underneath, and then there's the layer sandwiched in between. And these have an area A and a thickness D. Okay, and we have most of this data, so we get 1.20 times 10 to the minus 4, that's C, equals, we've got the permittivity of free space, 8.85 times 10 to the minus 12. We've got the relative permittivity, i.e. the dielectric constant, being 10. And we've got the area, which we don't know, all divided by, and we've got the thickness of the material, 2.00 times 10 to the minus 3. And we just check our units, it's in meters. So we're all good to go, and we should get an answer in meters squared. Everything has to be in SI units for this equation to work. We've got an area thing on the top, which is a meter squared. We've got a meter on the bottom. One of these other units must have a meter built into it, so we've got to make sure we keep this in our SI units, meters. So we get A equals 2.00 times 10 to the minus 3 times 1.20 times 10 to the minus 4 divided by 8.85 times 10 to the minus 12. And we do the calculation correctly, and we get 2711.9, or 2710 meters squared. This calculation, just be careful of your exponents in your calculator. It's very easy when you're dividing by an exponent to accidentally have your calculator not produce the right thing. This answer for an achieved point, that's the budget question of the 4 parts of this question. And this brings us to the last part of the last question of this exam paper. What have we got? So we have this circuit here. Describe the direction of motion once the capacitors are connected together. Now we can say the charge is going to flow from more charged to less charged. That's one possibility. We can also think about the current. So positive charge flow is going to go from here to here, which is a clockwise current. which is, if we think about electrons or anti-clockwise flow of electrons. Right, anti-clockwise flow of electrons. Either of those would obviously be sort of fine. Could also say from A to B, or left to right. Lots of ways of describing what's happening with the charge. Now, so those are some possibilities. That only gets us this, which is probably going to be an achieved point. By calculating the total charge, show that the common voltage that each capacitor has once equilibrium is reached is 45.5 volts. So show that. So we're not going to get any credit for 45.5. We're going to get credit for calculating it. So show that. Now, let's see. We can work out the charge on each of these capacitors. You go to your formula sheet, you find a formula Q equals CV. That's a formula that relates the amount of charge on the capacitor with the capacitance and the voltage. So we can do this twice, or we can do it once to find the total if we want. Well, we can do Q1, or QA rather, equals CAVA, and that's 50. 50 is the voltage. 1.20 times 10 to the minus 4 times 50, and we do the calculation and we get 6.00 times 10 to the minus 3 coulombs. We can do the same thing for QB. 40 times 1.00 times 10 to the minus 4. 4.00 times 10 to the minus 3 coulombs. The total charge, add them together, we get 10.00 times 10 to the minus 3 coulombs, which is also the same thing as 1 times 10 to the minus 2. Okay, so that's a possibility. Total charge. Now, what have we been asked? Show that the common voltage for each capacitor. So now we need to know, so we're going to do Q total equals C total times V total. Here's a good place to go, right? Now, what we need though is we need C total. So C total, and the key thing here is, are these in series or in parallel? And what I'd like you to think is that once we've got these connected and they've equalized, the voltage drop across to them is the same, which is the same characteristic you would have in a parallel circuit. In a parallel circuit, V here and V here, call them V0 and V1. The voltage difference between here and here is the same as the voltage difference between here and here. In a series circuit, that wouldn't necessarily be true. In a series circuit, you could have different voltage drops across them, right? Depending on their capacitances and so on. So this is a parallel circuit because the voltage across the two capacitors is the same. C total equals C1 plus C2 in a parallel circuit. So we get Q total, which we've got down here. So 1 times 10 to the minus 2 equals, and we've got two capacitances, 1.20 times 10 to the minus 4 plus 1.00 times 10 to the minus 4 times V total. And now we get V total equals 1 times 10 to the minus 2 divided by 2.2 times 10 to the minus 4. We do the calculation, we get 45.4545, which we round to 45.5. This 4 here rounds up. Volts. Okay, so crucial you put this down so that it shows that you're getting to here. Crucial you show all the steps really, so you're getting to there. And hence, we've still got one more step, hence calculate the charge on the cap. So QA equals CV equals 1.20 times 10 to the minus 4 times 45.5, which is 5.45 times 10 to the minus 3 coulombs. Now, if you hadn't managed to work this out, you could still do this. You could still have worked out the new charge on capacitor A as long as you had this formula, which gives you a lot of options for getting some points here. I'll show you why. In this question, lots of things were potentially worth achieve points. To start with, all of this was worth an achieve point. Any bit of it, sorry. This was worth an achieve point. This was been worth an achieve point. This would have been worth an achieve point. This or this. Any of those could have got you an achieve point. Similarly, this could get you an achieve point, or this also could get you an achieve point. The total charge here could get you an achieve point. The calculating the total capacitance was worth an achieve point. So lots of possible things were achieve points, but to get, and then they have these really confusing combinations, you needed, basically this wasn't really useful, this part wasn't really useful unless you're looking for achieved. For the merit, you needed this, Q total, or this, so that or that, plus this correct calculation, or this correct calculation. So you needed two correct calculations that were important in the process, and for excellence you needed all four parts, which is really just to say you needed to get to the correct answers through each bit, which is not really that hard. This was nicely broken down for you. Okay, so I hope you've worked your way through these now and seen not just how each question can be completed, but also how the marking guide works. What I think you may realize from this is that the space provided in lots of parts of the exam paper is really quite insufficient for the task and the amount you might need to write. Make sure you use the extended paper at the back of the book. It's a really good reason to do these exam papers actually in your exercise book, so you get used to writing fairly complete answers and not being put off by the small spaces provided in the exam. Thank you for your time.